Good evening everyone. Now we shall see what is process synchronization. Process synchronization. As we have already studied the types of processes, there are two types of processes. One is cooperating process, another one is non-cooperating process. Cooperating processes are those processes that can affect or be affected by other processes executing in the system. Say suppose for example, consider there are n number of processes, process P1, P2 up to Pn processes. If all these processes share a logical address space or share common data through file or message, then all these processes are said to be cooperating processes. That means that if process P1 is affected, then process P2 will be affected. If process P3 is affected, process P2 is affected, process P3 is affected, and so on. So when the processes are going to share same logical address space or share same data through file or messages, they are said to be cooperating processes. Say suppose for example there is a resource which should be shared among process P1 and process P2. The same resources should be shared between these two processes, and there is a condition that these two processes cannot access the same resource at same time, or concurrent access of the shared data may result in inconsistency. Concurrent access to shared data may result in inconsistency. In order to avoid this data inconsistency, there should be the synchronization between two processes. I repeat, in order to avoid concurrent access, that is accessing the same resource by P1 and process P2 simultaneously, which may lead to data inconsistency. In order to avoid this data inconsistency, there must be process synchronization between process P1 and process P2. Next, we shall see an example of producer-consumer problem, which is a classical example problem for process synchronization. This problem says that there are two persons, one is producer, one more is consumer. This producer will produce the items. This producer produces the items into the list, and consumer consumes the item from the list. That is, suppose that the illustration of the problem says that suppose that we wanted to provide a solution to the consumer producer problem that fills all the buffers. We can do so by having an integer counter that keeps track of the number of full buffers. Initially the counter is set to 0. It is incremented by the producer after it produces a new buffer, and is decremented by the consumer after it consumes a buffer. That is, what is this? Whenever a producer produces the list of items, I repeat, whenever the producer produces list of items, the items have been incremented, that is, items have been put inside the buffer through incrementing the variable called counter. Initially the counter value is 0. Whenever producer inserts an item, the counter value will become 1. That is, counter plus plus happens. Incrementing the counter happens in producer part, and whenever the item is added into the list or buffer, the consumer can consume the item and the buffer value will become, the counter value will become decreasing. That is, the counter value is decremented at the consumer side. And there is a condition that synchronization means there should be an understanding. So concurrent access cannot take place between producer and consumer. In order to avoid this concurrent access, we should have certain synchronization between producer and consumer. Simultaneous access of the items inside the buffer is not allowed because we cannot keep track of the counter value. So this problem of producer consumer leads to a definition called as race condition. That is, it is a situation where several processes access and manipulate some data concurrently. Some data concurrently is trying to access the counter value, trying to access simultaneously, trying to access the items present inside the buffer, which will affect the counter value, and manipulate some data concurrently. And the outcome of the execution, depends on the particular order in which the access takes place, and the outcome will result in a particular order in which the access takes place. So in order to avoid this, there should be a synchronization between your producer and consumer. Same explanation is being explained with the help of program. Here, until the condition is true, your buffer size, counter equal to buffer size, you're going to produce an item, you're going to increment the value of your counter. Next, counter plus plus. Next, with the help of your consumer, and when the counter is 0, you will not have any items inside the buffer. Whenever the buffer is full, you will try to access the item. Then whenever you try to access the item from the buffer, you are going to decrement the counter by telling that you are going to consume the item. Consuming the item. So next we shall see what is critical section problem. Critical section problem. So in critical section problem, as we can see here, first consider system of n processes, that is P1, P0, P1, P2 up to Pn minus 1 processes. Each process has critical section segment of code. Critical section segment of code. That is, what is this critical section of code? What do we mean by critical section segment of code? Is that in this critical section, whichever process wants to access, the process may change common variables, update table, writing a file, etc. When one process is inside the critical section, no other processes can enter the critical section. So it is critical section is to design the protocol to solve this. That is, each process, whenever I tell that a process is executing in its critical section, it should undergo three major sections in order to enter the critical section. The first section is called as entry section, which is followed by exit section and then reminder section. What is this? We shall see in next slide. The general structure of process Pi. That is, whenever I tell process Pi wants to execute, it should first come into the entry section. What will this entry section do? It will give a lock to the process to enter critical section. It gives the lock to the process to enter into critical section. Next, inside your critical section, whenever process Pi gets the lock, only that particular process will be executing. Only one process can enter. That is, only process Pi can enter and it can execute here. After the execution is over, it will exit from that particular section. It will exit from critical section by telling that remove the lock. Exit section. By entering exit section, it will tell remove the lock given to me, that is process Pi, remove the lock given to me, and then the reminder section, whatever is the remaining code of that particular process, that particular code will be executed, and this will be repeating until the condition is true. This is the general structure of process Pi. Next, in order to have this general structure, there are three conditions to be satisfied. The first one is mutual exclusion, second one is progress, third one is bounded waiting. What is this mutual exclusion? As I told, mutual exclusion, the important characteristics of critical section problem is that you should see to that only one process is going to execute at a time. Only one process is going to execute at a time. No other processes can be executing. When process Pi is executing in its critical section, no other processes can execute in the critical section. That is called as mutual exclusion. Progress. If no process is executing in its critical section, then there exist some processes that wish to enter into their critical section. then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Means that assume that there are three processes, process P1, P2, P3. Among these three processes, no process is executing in its critical section. At that time, what happens? P3 will be willing to enter to its critical section. When P3 is wanting to enter into the critical section, the lock should be given to it. That is, the entry section should be given to that particular process P3. The critical section entry should not be postponed indefinitely. It should not be postponed. The lock should be acquired, or the lock should be given for process P3 to execute in its critical section. And last one is bounded waiting. Bounded waiting. Bounded waiting, what it does, it will keep track of the number of times that the processes are allowed to enter into their critical section. Critical section. After a process has made a request to enter its critical section and before that the request is granted. It will keep track of the number of times the process is going to enter into the critical section. And always remember that whenever your processes are running in your critical section, it should always mandatorily satisfy first two conditions. The first one is mutual exclusion, second one is progress. Bounded waiting condition is optional. Bounded waiting condition is optional. Because in your gate question, they will ask telling that what are the three conditions or what are the conditions to be satisfied for a process to enter into its critical section. When such question is asked, you should tell that mandatorily mutual exclusion and progress should be satisfied. Bounded waiting is optional. Bounded waiting is optional. So remember that these two conditions are mandatory for each and every process to enter into its critical section. Now next we shall see what is Peterson solution. Peterson solution. What is this Peterson solution? Peterson solution is an good example. It is a good example for your critical section problem. It is a software based solution. It is a software based solution to critical section problem, which is known as Peterson solution. And this Peterson solution is always going to implement only on two processes. That is why it is called as a two process solution. That is why it is called as two process solution. So what is this two process solution? Here, in order to give solution, we should keep track of two shared variables. The two processes share two variables. The first one is int return. Second one is boolean flag. What is this return variable going to do? This return variable will tell which process is going to enter the critical section. This process is going to tell us this variable turn is going to tell us which process is going to enter the critical section. And next, boolean flag variable array. This array will keep track, or it will indicate if that particular process or which process is ready to enter into the critical section. Variable turn will tell us which process is going to enter the critical section, whereas flag array is going to indicate which process is ready to enter the critical section. Say suppose if turn equal to I, then process Pi is allowed to execute in its critical section. The flag array is used to indicate if all the process is ready to enter into its critical section. In order to enter the critical section, process Pi first sets the flag array. Process Pi will set the flag array to true. Then it sets the value of j. The turn variable will tell which process is going to enter, and thereby checking the condition, it will tell the process Pi can enter into its critical section by making flag of I equal to false. Then after the execution is over, until the execution of process pi is done, flag of I will be true, that is process pi is executing. Once the process pi completes its execution, flag of I will become false and the remainder section, that is the remaining code of process pi is executed. This is the algorithm for process pi, or general structure of Peterson solution for process pi. Next, we shall see what is synchronization hardware. Now, whatever solution till now we have seen is a software-based solution. It is a software-based solution, and this software-based solution, that is your Peterson solution. Peterson solution is a software-based solution which will not guarantee that it will work on modern computer architectures. So, instead of that, we can generally state that any solution to the critical section problem requires a simple tool called lock. Any solution to the critical section problem requires a simple tool called a lock. That is how it is. Same thing, instead of entry section you have acquire lock. So you are going to tell the processes to first acquire the lock. After acquiring the lock, enter into critical section, then release the lock, then execute the remaining code and complete the execution and come out. Now we shall see what is this test and set instruction. Test and set instruction is nothing but tells that what type of variables are going to be executed. That is, it tells that the important characteristics of this instruction is that it is executed atomically. Thus, if two set and test instructions are executed simultaneously, then they will be executing sequentially in some arbitrary order. That is, executed atomically, returns the original value of past parameter, sets the new value of past parameter to true. Why are we going to use this test and set instruction is that many modern computer systems provide special hardware instructions that allow us to test and then modify the content of a word, or to swap the contents of two words atomically. This is the major use of your test and set instruction. I repeat, many modern computer systems provide special hardware instructions that allow us to either test and modify the content of a word or to swap the contents of two words atomically. When this is going to happen, it will be an uninterruptible unit. It is called as an uninterruptible unit. No other processes can interrupt in between. So, how does the structure of process pi look? This is how the process of pi looks. That is, when test and set of lock is there, do nothing, enter the critical section, lock equal to false. After the process pi is executed, you tell lock is false, then remainder section and come out. Next, what is this swap instruction? Swap instruction operates on the contents of two words. Swap instruction operates on contents of two words. Contents of two words. Contents of two words, that is boolean A and boolean B. It is going to operate on the contents of these two variables. So, how does the process or general instruction, or if in case the system supports your swap instruction, if the system supports swap instruction, then we can say that there is a mutual exclusion property to be provided. Mutual exclusion property can be provided for the process PI. So when mutual exclusion is provided for process PI, this is how the general structure of your process PI looks with respect to swap instructions, with respect to swap instruction. Next topic is semaphore. What is this semaphore? Semaphore is an synchronization tool. It is a synchronization tool. It is a synchronization tool, and here we always use a single variable s, which is an integer variable, that can only be accessed via two operations, One is wait operation, another one is signal operation. What does this wait operation and signal operation do? As we can see here, wait of s, where s is a semaphore. Wait of s, we are going to decrement the value of semaphore. While s is less than or equal to 0, decrement the semaphore value. Whereas using the signal operation, I am going to increment the value of semaphore. That is signal of s is a semaphore, increment s plus, increment the value of s. So two things to remember. One is s is a semaphore, which is an integer variable which can be accessed by only two operations. One is wait, another one is signal. Then what does your wait operation do? Second point, your wait operation will decrement the value of semaphore s minus minus. Your signal operation will increment the value of semaphore s plus plus. So always remember that whenever the modification is going to happen for your s variable, you should see to that the modification to the integer value of semaphore to the wait and signal operation must be executed indivisibly. That is, at a time only one process can make modification for the same semaphore. Next, types of semaphore. There are two types of semaphore. One is counting semaphore, another one is binary semaphore. Counting semaphore, what it will do, it is an integer value that can range over an unrestricted domain. And binary semaphore, it can have only two values. One is 0, another one is 1. And remember, it is also called as mutex lock because this binary semaphore provides mutual exclusion condition, which is one of the solution for your critical section problem. So remember that binary semaphore is also called as mutex lock because it provides mutual exclusion condition. Next, how do we make use of these two semaphores? For example, consider process P1 and P2. It tells that S1 to happen before S2. That is, assume that process P1 is going to execute semaphore S1 and process P2 is executing semaphore S2. And it tells that S1 to happen before S2. So how can we write the code now? We are going to write the code with the help of our two operations. As we have seen, two operations are your wait and signal. What will your wait do? It will decrement the value. Your signal operation will increment the value. Now if we see here, initially synchronization, take a variable called as synchronization, initialize that to 0. Initialize that to 0. So when I tell process P1 is executing, semaphore S1 will be executing. Semaphore S1 will be executing. It will provide a signal. It will provide a signal with the help of synchronization. With the help of synchronization variable, wherein it will increment the value to 1, telling that process P1 is executing or semaphore S1 is executing. After the execution of this, process P2 can start its execution by telling wait or calling your wait synchronization operation. This wait synchronization operation will decrement the value to 0. And ask semaphore S to continue the execution. That is the major indication for process P1 and process P2 to execute their respective semaphores. With the help of your synchronization variable, S1 is going to give a signal telling that the value is incremented to 1, incrementation operation with respect to signal operation, and decrementation operation with respect to wait operation. So this process P1 and P2 can execute their semaphore S1 and S2 only if we see here, it is 0 and 1. The value of synchronization lies between 0 and 1. As we have seen the types of semaphores: counting semaphore, binary semaphore. Binary semaphore, it can range only between 0 and 1. So this type of example or this type of semaphore can be done only if it supports binary semaphore or it implements binary semaphore. This can happen only by implementing your semaphore with respect to binary semaphore. So after this, there is certain disadvantage of your semaphore, that is called as busy waiting. That is, when a process is in its critical section, only other process that tries to enter its critical section must loop continuously in its entry code. That is, meaning is that whenever process P1 has entered in its critical section, other process tries to enter its critical section, but until the execution of P1 is over, P2 will continuously keep waiting inside the entry section itself. It is going to loop continuously in its entry section. That is the major disadvantage of your semaphore. The major disadvantage of semaphore is busy waiting. So in next lecture, we shall see the remaining classical problems of synchronization, that is bounded buffer problem, reader writer's problem, dining philosopher problem. Thank you.